So it's the top of the hour. I think we can get started. Hello, everyone, and welcome to the August webinar presentation for the Underground Construction Association Young Members Group. My name is Tony Bauer, and I am one of 3 members of the UCA of SME Standing Committee for the UCA Young Members. I am the chair, and I'm joined by Aaron Clark, the Professional Development Chair, and Shannon Goff, the University Outreach Chair. As always, please join us for our webinar series on the last Wednesday of each month. Next month, on September 30th at noon Eastern Time, Nasri Munfa, Senior Vice President at HMTB, and Wojciech Gall, Principal at Gall's Consultants, will present on the Eurasia Tunnel as part of the Istanbul Strait Road Tube Crossing in Istanbul, Turkey. As always, you can register for next month's webinar on the events page at our website. Today, we continue the webinar series with a presentation by Luis Piek on the Lake Mead Intake No. 3. The project was recently successfully completed in December of last year. Luis obtained a Bachelor's of Science in Applied Mathematics and Engineering Sciences in 1998 and his Master's in Structural Engineering in 2004 from the University of California in San Diego. While working abroad, Luis obtained his Master's in Tunneling and Underground Construction from the Politecnico di Torino in 2008. His work has taken him across the United States, Europe, Australia, and Asia. He currently resides in San Francisco, and he is the Geotechnical Design Manager for the San Francisco Central Subway Project. Luis, thank you very much for presenting to us today, and when you're ready, you can share your screen.
Thank you very much for that introduction, Tony. Today I'll be presenting on Lake Mead Intake No. 3, which was, as you mentioned, recently completed the hole through in December of 2014 last year. It's a really challenging project. It's pretty much unprecedented in the world of tunneling in terms of its external pressure, as well as some of the design and engineering challenges it faced. This presentation will go through some of these briefly, but if you have any further questions, I have a slide at the end that will have my contact information. So to start, the organization of this project, SNWA is the owner of the project, with Parsons as the construction manager and the owner's engineer of CH2M Hill and Montgomery Watson Harza. This project was originally released as a design build, with the successful bidder being Vegas Tunnel Constructors, which consists of the Improgilo and S.A. Healy companies, Arup as the lead designer with Firely Associates as a major sub. So Lake Mead is located approximately 35 miles directly to the east of Las Vegas and provides basically, for all intents and purposes, all of the water that's used in Las Vegas for drinking water, irrigation, and so forth. The amount of people that have serviced by the SNWA has grown exponentially, and as such, so has the water usage over the years. Between 1997 and 2006, the system capacity more than doubled by the addition of another intake on Lake Mead to go ahead and deliver water to the treatment plant and into their distribution system. This graph here shows over the last 100 years the dependency on Lake Mead by the city of Las Vegas. Originally, Las Vegas was supported primarily by spring flows and groundwater. However, around 1950, the amount of water provided to Las Vegas by Lake Mead has grown tremendously, as you can see in this graph. Starting around 2000, we entered into probably one of the worst droughts in recent history, and some of these photographs illustrate just how dramatic it's become, with the water dropping nearly 140 feet between 2000 and 2015. You know, it's really obvious in the lower right-hand corner to see just how much the water lake has dropped. And to give a size comparison here, this is a person in a boat down here next to the bottom of that rock outcrop. Here, this slide basically illustrates the levels of Lake Mead as well over the last 90 years here. Essentially, we are at the lowest level of the lake since it was initially filled in the late 1930s. So it was a dramatic look forward that SNWA had to come to terms with the idea that lower lake levels could affect their water intake supply. Essentially, Lake Mead has two existing intakes. One of them is located at about elevation 1050. What happens is as the lake level drops, you can't continue to utilize your intakes if they're within a certain elevation of the surface, because the amount of debris and material in the top layer becomes prohibitive to actually treat and put into your delivery system. Currently, the lake level is at 1075. However, if that would have dropped another 25 feet, intake 1 would become out of service and essentially cut in half the amount of water that the SNWA is able to take out of the lake. Another 50 feet beyond that, intake 2 would then go out of service, and the city of Las Vegas would have to resort to very dire measures. So considering that the lake had already dropped 100 feet by the time this project was initially conceptualized, this was a very realistic look forward, and the Lake Mead Intake No. 3 project was born. The idea behind Lake Mead No. 3 was to add a third intake to the lake at a much deeper elevation, an elevation of around 860 at one of the deepest locations in the lake. Not only would this provide long-term solutions to Las Vegas's water resiliency, but also putting the intake at the deepest part of the lake means that the water quality is higher in these locations, and it would require less water treatment actually. So this is a schematic essentially showing how the intake 3 will link to the two existing intakes and then go out to the water treatment plants that are nearby. The overall objectives of this project are to protect the system capacity and access better quality water at the deeper part of the lake and prepare for inevitable future drought cycles. I think that we have come to the conclusion that this is not an isolated event, but that we need to look forward to the future and be able to design for these type of things to occur in the future. The bidding process was a design build where qualified firms were first shortlisted, and then final bids were put in and presented with the combined technical score of managerial experience and price coming together to determine the best offer. As a design build, the contract did allow for refinements of the shaft and assembly cavern, the tunnel alignment, segmental lining design, and the final intake connection. And in March of 2008, Vegas Tunnel Structures was successfully awarded the design and construction for a contract price of $447 million. So what I'm going to do is talk a bit about the optimizations that were done as part of the design build project and get into some of the key aspects. So initially the project starts out with a onshore shaft, which is 30-foot diameter and 600 feet deep, where at the bottom you construct a assembly chamber for the TBM and you launch the TBM out of a starter tunnel. Then you follow that with a 3-mile, 20-foot internal diameter tunnel that has to be excavated underneath the lake so that the pressures, the water pressures on the TBM were up to 15 bars working. And at the end of the project, you have to hit a 100-foot tall precast intake structure sunk on the bottom of the lake. So all in all, a pretty challenging project and pushing the limits of TBM technology and engineering design. So the access shaft, like I mentioned, was about 600 feet deep, and it consists of a couple of different little portions. The access shaft itself, a temporary niche tunnel about 150 feet down, and then a secondary connection to the intake pump station 3 that would connect to the rest of the system there. The TBM assembly chamber at the base with the starter tunnel and stub tunnel for future expansion if necessary in the future. So one of the things that we looked at was the geology of the area, which was primarily fairly good rock, although it did have a large feature of the detachment fault, which separates the upper and lower plate of Saddle Island in the local area, as well as several jointed systems that actually conduct water and into the excavation. So the way that the shaft was optimized was by adopting what we call a top-down construction method, where essentially you're casting the permanent structure as you go. The way that works is you would drill out the round, perform a blast that would go ahead and excavate down usually about 10 feet per lift. Then you would excavate down. This picture shows an excavator pretty much bottomed out with the some of the first castings of the shaft just starting there. The idea behind the top-down construction was you could map the rock face and install initial support. And because the initial support only needs to provide basically rock protection for the cycle that precedes it, the amount of mesh and rock bolts could be minimized. Not only that, the shaft was designed to be open for several years, and as such, you don't want to have to design initial support to last for that long. After you go ahead and install that initial support, you lower the form down in place and you cast concrete, and you basically repeat the cycle over and over again as you go down. So over here you can see the rings of the shaft and all the lifts that were associated. These are about 10-foot lifts as we went down. Just some more photos here, a little bit larger for people to see. This is the form in place, getting ready for concrete. We used a 3-arm drill jumbo Terex system to go ahead and drill out the round to go ahead and set everything ready to blast. Here's another photo showing, I guess this is about the 7th lift now, and a picture of some of the concreting works with the shaft well underway at this point. The next thing that needed to be built was the TBM assembly chamber. We specified this again as drill and blast construction using a top heading and bench with pre-excavation grouting where required to go ahead and provide that water cutoff. The way this was designed was we initially put up a initial shotcrete lining that was supported with steel rock bolts. But because we wanted to create a permanent structure as well, this was followed by permanent fiberglass rock bolts and a final shotcrete liner. This allowed VTC to speed up excavation and construction and meet the requirements of the project. Additionally, we designed the cavern as a drain structure, since designing it as a tank structure where you try to prevent the water from actually entering into the excavation under basically maintenance conditions would have resulted in this lining being very thick. We designed this as a drain structure for structural efficiency and essentially put weep holes through the lining out into the rock so that during drawdown conditions the lining would not actually take the water pressure, which would have been the majority of the load case in this case. So just some photographs of the heading and bench excavations in the cavern. You can see the shaft up in the upper left-hand corner, and the drill jumbo out in front. Here's a picture of some of the guys on VTC drilling and loading the face, and a shot from the other side giving you an idea as to kind of the width of the cavern and the size. So after this was done, after the top heading was taken, we came back and did the bench, which then ended up looking something like this. Looking back, we strung up some waterproofing to go ahead and just make it a good, clean working area for preparations of lowering the TBM. But prior to that, we needed to go ahead and create space out in front of the cavern for actually the length of the TBM. The TBM is 600 feet long, and so it required a starter tunnel to be built. So initially, the starter tunnel was in alignment with the cavern. This is a picture in June of 2010 of basically just the turning under of the starter tunnel. But within about 4 months of time, the ground had significantly changed from the expected conditions to material that was not a drill and blast type material, but more a fault gouge material that was requiring being excavated with basically a bucket excavator. You can see in this photograph, basically the excavator had come up previously to the front and taken out a bit. So essentially, fast forwarding over the next 6 months, this starter tunnel was not successful and had to be abandoned, and a new starter tunnel had to be built. This is some of the sample of what some of the material in the face looked like. This is a myelinized amphibolite. It's basically almost like a fault gouge. You could easily break it with your hands. So, like I mentioned, the starter tunnel, that starter tunnel was not successful and was abandoned, and a new starter tunnel begun in February of the following year, with that being a drill and blast with pipe canopy, steel arch forms, and shotcrete. This photograph shows the pipe canopy coming over the top of the tunnel. The design was very robust in that we only had limited rock information due to the horizontal coring that was done prior to the start of this new alignment, and we needed to be prepared for almost anything that the project could throw at us. SMWA were fairly adamant that the solution had to be robust enough to handle anything, because they were on a bit of a time crunch in terms of the water in the lake continuing to lower over time, and the need for this project to come online to provide that redundancy to their system. So this was the approach adopted to go ahead and perform this starter tunnel. Some neat folding of the face was encountered. We did encounter some fault planes and some interesting features as we went along here. This photograph shows the steel arch and some of the rock face conditions that were encountered. Another photograph showing the drill jumbo that was used, and the surveyor here in the foreground getting ready to shoot where the pipe canopy locations go in. This is a photograph of some of the intrusives that we found in the face of the tunnel, and some of the folding that had occurred hence. And so after the starter tunnel was successful, we had to get ready to start with the TBM. The TBM has a 24-foot outside diameter. It's 600-foot long trailing gear with a total weight of about 1,500 metric tons. The TBM is designed to be driven actively up to 17 bars of pressure. So it had to be operating at 17 bars and not just holding steady. For comparison, the previous project that came close to this was the Holland Sauce project, which was designed to be static up to 11 bar and active mining at 9 bar. So effectively, this project doubled the external pressure that was going to be seen as the project progressed. The machine is also capable of grouting and ground improvement ahead of the face, which was important because there is no ability to create an access shaft on this project. You're underneath the lake bed, you're very deep, it's under high pressures, so effectively anything that needed to be done to the machine had to be done underground. And the machine for that purpose was designed and fabricated specifically for the project with some pretty hand-in-glove coordination between VTC and Heron Connect, who were the supplier of the machine. The principle selected for the project was to have it operate in a couple different modes where the rock is very fractured and communication with the lake could be expected. The machine was designed to operate in slurry mode with a traditional slurry circuit. However, there were portions along the project where the ground was had a permeability that was fairly low and could allow for open mode excavation. To allow for this, the TBM was designed essentially as a hard rock machine, but with a long horizontal screw conveyor that went down through the center of the machine in order to allow the materials in open mode to be basically evacuated onto a conveyor belt and taken out of the out to the shaft. Here's a picture of the TBM under partial assembly on the surface. The TBM was partially assembled after being commissioned and shipped from Germany and lowered down effectively in pieces and fully assembled in the cavern prior to being pushed forward. So here's some photographs you can see here. The pieces being lowered down into the cavern, and the picture in the lower right-hand corner is with the machine almost fully assembled, minus the tail shield. Here's a picture of the TBM. Her name is Kokopelli, which is the Hopi god of rain. And you can see her being pushed forward here on some ALE jacks being just slowly pushed into place and getting ready for launch. So just as a review, the launch location was over on dry land in the purpose-built shaft and cavern. And the overall alignment has the tunnel coming out and turning to the right to avoid some of the volcanics that were encountered in this area out here during the initial drilling program and ground investigations. The alignment continues out underneath the lake before turning right again and heading straight out toward the intake structure location. This is basically a profile showing some of the geology of the area. The tunnel is approximately 3 miles, and it starts out on a very low 1% slope before getting underneath this very deep feature, which is the Las Vegas Wash, which is basically the wash area where all of the previous water that would drain from the Las Vegas Basin would dump into the Colorado River. This feature essentially limited where our alignment had to go to safely pass underneath at this location with enough rock head to prevent any type of instability of the tunnel face in this area. After that, it continues at a 3% grade to the intake itself. So some of the geologic conditions that were encountered along the project. I talked first about the upper and lower plate of Saddle Island, which are two distinct different types of rock. The upper plate is essentially a quartz feldspar gneiss with mica schist, and the lower plate has some pretty hard myelinized amphibolites. The upper plate was very brecciated and required us to essentially mine always in closed mode. The next major feature was the Muddy Creek Formation. This is a conglomerate and basically a sandstone and siltstone that had varying levels of induration or cementation. And this was mainly the material that could be excavated in open mode because of its weak behavior. It actually has the ability to heal itself and actually didn't exhibit a lot of groundwater inflow, in fact, nearly none. The next major geologic feature was the red sandstone. And again, this is a conglomerate, but had a higher amount of iron oxide. And again, this was a softer rock material that actually was able to be mined mainly in open mode as well. And then you have the Las Vegas wash, again, in this area. And you always save the best rock for last, right? So the finished area around the intake was actually tertiary basalts, and they were both vesicular and non-vesicular. So you can imagine at the end of the project, you're mining into material that has pathways that can directly communicate to the lake. So you have high pressures that will be active at the very end of the project. And this last part was mined again in closed mode. So a bit about the precast segmental lining, which was my main contribution to the project. The precast lining was cast at a purpose-built facility about 35 miles from the job site, and we used traditional reinforcing for these with 6,000 psi concrete and 80 ksi yield strength steel. One of the interesting things about Las Vegas is that most people associate it with being very hot, but in fact it can get extremely cold in the desert, and in fact we did actually have snow at the job site once over the course of the project. So both hot and cold weather curing needed to be considered due to that large temperature swing of the Las Vegas region. Now, one of the interesting things about the project as a designer is that essentially you normally design segmental linings where they have very low axial forces but very high bending moments, especially for soft ground areas. And so normally you'd see a clustering of the design cases out around this area. But in fact, on this project, it was quite the opposite. What we saw from the use of our closed form spreadsheets, our beam spring models, and our structural modeling was that, in fact, the majority of the load cases resulted in extremely high axial loads up to the limit of the capacity of the segments with actually very low bending moment. And primarily that had to do with the high amount of water load and the deep nature of the tunnel. We used a variety of tools to analyze the lining, and all of them really do have their place, even in modern engineering. We used everything, like I mentioned, from closed form spreadsheets to beam spring models, some fancy structural modeling software, and some ground modeling software. But you can always use these to basically calibrate yourself and cross-check to make sure that actually you're getting the right behavior out. I can't stress enough to young engineers that you don't want to always just jump to the neatest looking tool that produces nice colors to go ahead and do your structural analysis. But it's also important to use closed-formed empirical solutions that have preceded all of the fancy software to go ahead and make sure that you're intrinsically getting the right feel for the design, as well as going ahead and cross-checking and double-checking that your modeling software is actually behaving correctly. So due to these high axial loads that were going to be induced on the tunnel lining, there is a phenomenon called bursting that is present in the joints, which basically causes catastrophic rupture of the concrete. The picture on the right-hand side here is actually a full-scale test that was done at the University of Illinois as part of the Arrowhead Tunnels project. And in fact, they were showing this basically is mid-explosion, showing how the concrete basically spalls off under these high load conditions. As such, we spend a lot of time detailing the reinforcing to address not only this bursting force, but due to the high pressures that the tunnel had to be driven at, there's also high jacking forces that the TBM induced on the tunnel lining that needed to be addressed. And it was a similar process for the jacking forces that we used to design out these segments. Some pictures of the segments delivered to this job site here. The segmental lining is a 5+1 system with some interesting dowel connectors between it and bolts, both radially and circumferentially, to hold the system together. A picture of the job site here, basically showing the segmental lining yard and the shaft up here in this location, followed out by going ahead, and the tunnel basically traversed the saddle island here, and then going out, and the intake out being somewhere out in this general area. So that said, I think I would like to talk a little bit about what I think is the most interesting part of this whole project, which is the intake structure. Again, this is a design-build project, and there were only a few ideas that were presented during the bid phase and the RFP that were available to be reviewed. The reference design had a approach that was previously used on one of the previous intakes, and the idea behind this was that you would go ahead and you would, ahead of the TBM arriving, you would go ahead and drill down into the lake bed, and you would embed a steel pipe into the lake bed and perform backfill concreting operations, and going ahead and then putting in concrete piles below the lake to go ahead and ensure a water cutoff. You would then go ahead and drive the TBM past this steel pipe, and then, as you can imagine, very carefully excavate upwards into the steel lining, and finally make the connection to the intake. This not only was difficult to foresee how it would be constructed, but it included some very inherent design risks and construction risks. You can imagine that this is at the very end of the project, and you're exposing people to potentially very high pressures right at the end of the project. And it would also require some pretty specialty drilling rigs in order to go ahead and and perform this type of work, and probably require hard hat diving and all sorts of other things that were, if you can, as designers, you want to try and avoid. So the solution that was presented by the VTC Arup team at BID was to move away from actually trying to do any drilling on the bottom of the lake and setting of things, and instead to excavate a large pit. And you could basically take a steel elbow, if you will, and embed it on the bottom of the lake, and then drive your TBM into this intake and go ahead and dock it. And this would prevent you from having to do any type of underwater hard hat work or exposing workers to any type of high pressures, because the TBM itself is designed to actually address these high pressures. So at BID, we designed this out as 100% stainless steel structure. However, as we progressed in the design after award, we started taking a look into the use of precast concrete. And in fact, that's what we ended up using, was a large precast base followed by a stainless steel riser pipe and the intake screen. The advantages of this is that the underwater excavation and installation of the intake structure occurs way before the arrival of the TBM. And this takes it off the critical path and goes ahead and reduces a lot of time as well by going ahead and having it prefabricated on a specialty built barge. The entrance allows the TBM to come into the structure and do dewatering in a controlled way. And in that way, in that manner, if you do detect leaks, you have the ability of going ahead and sealing those defects prior to going ahead and again trying to draw down the water and seeing if that sealing was effective. It reduces the amount of activities both at the riser site and on the lake surface. It minimized the amount of underwater construction and diving operations, and in fact there were no hard hat diving required. The intake is about 100 feet tall. It's 8.5 meter internal diameter, weighed 1,600 metric tons, and had a buoyancy weight of 1,000 metric tons, which is important because we ended up using that approach to do the construction of the intake. So a marina was built at the job site, and a large crane and barge system were put together to go ahead and assemble and precast the intake. For comparisons in this slide, right down here is a little person, just to give you a scale of what we're looking at here. So in the first stage, the base slab was cast, and followed by the chamber structure and the TBM soft eye basically cast into the front of that using GFRP. We then lowered the chamber into the lake to take advantage of that structural buoyancy and help reduce the loads that were on the barge. Next, the top of the chamber was cast, followed by placement of the concrete cast collar, and then finally the riser section assembled, and the intake screen, and then essentially the structure was floated out into position and ready to be sunk on the bottom of the lake. So here's some photographs of the intake structure as it was being assembled. Some pretty heavy reinforcing of the exterior structure here, and this was designed by our Houston office. Essentially, we borrowed a lot of technology used from the offshore oil business in order to go ahead and look at how we could design this thing. They have gravity structures that are common practice in their field, and so we borrowed heavily from that in the design and fabrication of this intake structure. You can see in the front here, these are glass fiber bars This is the TBM soft eye. So forming up and getting ready for casting of that initial chamber. And this is what it looked like when it was stripped off. Pretty good concrete work. Excellent concrete work, actually. Followed by the cone, getting ready for the concrete collar and the intake here. I have to give great credit to Vegas tunnel constructors for their work on this in terms of figuring out the staging, the concrete mixes, how they were going to get everything formed and put together. As engineers, it's easy to put things on paper, but some of the real challenges come in building the project. It was quite a sight to see how all this came together, and you can see the intake structure itself here, getting almost ready to be floated out. This is a section of the stainless steel riser and the intake screen. And if you'll notice over here on the left-hand side, there's actually the bulkhead. This is a stainless steel bulkhead that would be put into place inside of the intake structure in order to provide the final plug. Really quickly, I'd like to talk about how we did the excavation at the bottom of the lake. Basically, there was about 6 inches of silt on the bottom of the lake, followed by 6 feet of old desert soil before getting down to rock. And that rock required actually blasting, underwater blasting, that was done from a crane barge, and then essentially using an airlift to excavate out the material that was blasted at the bottom of the lake. So essentially the way that this was done was blasting was done using shape charges, where an explosion throws an ingot of iron and steel down onto the rock, effectively cracking it, breaking it apart, and going ahead and allowing then the excavation to occur. The excavation was followed by a visual inspection with the ROV, a scan of the blasted surface, a redevelopment of the next blast and positioning, and repeating that several times. Again, no hard diving was required. Picture of the shape charges here, and a picture of the barge that was used as part of the lowering of the charges and the airlift excavation. Here's a side view of that barge with this long black pipe here being the airlift. And it's important to mention that it wasn't required to actually remove the excavated material from the hole, that there was an allowance for the spoil material to basically be stacked up on the bottom of the lake. So essentially this is the scan of the final excavation. You can see here in the middle of the screen the actual excavated surface, as well as the spoil pile here at the bottom of the lake. And so all that needed to be done now was to take a 100-foot tall precast concrete structure, float it out, and put it exactly in position. So here's the final assembly of the intake, followed by operations of floating it out and into place. And it was lowered using these very large, long strand jacks on all 4 sides, and lower it and down into place. This again required some pretty intensive marine engineering works by VTC to get it exactly into place and put down into position. Here it is going under, probably one of the last times it'll ever be seen by humans. until the TBM arrives, at least. And then followed by the Tremie concrete operations. This in itself was an incredible thing to do with basically an on-site batch plant being built, and then concrete trucks literally being put onto barges and pushed out to the middle of the lake, where they basically dump out of their chutes onto a conveyor system, and effectively this big arm here is the Tremie concrete operation as it goes underway. So just a little cartoon as to how all this came together. After completion of the excavation on the lake bottom, the structure was lowered into place, and the bulkhead, where I mentioned before, was left off. The bulkhead sits in this region right in here. The Tremie concrete was put into place, and that Tremie concrete was about 14,000 cubic yards, just to kind of give you a comparison as to what I was looking at here. Next, the TBM approached and was slowly guided into the intake. After TBM broke in, the bulkhead was put into place, and then the chamber was drained. Again, this allowed all these operations to occur without any manned entry, without exposing any workers to any high pressure conditions. Next, after the final connection was made, and we were assured that there was no leaking, we went ahead and the TBM was essentially disassembled, and a final concrete lining was put into place. Currently, the chamber is being flooded, and then once the pressure is balanced between the TBM, between the outside and inside, then the bulkhead basically comes right off. So just to animate that one more time, after you have equal pressure on both inside the tunnel and at the lake, this bulkhead just essentially will come straight off. This is, again, just a kind of another rendering of the final intake after the TBM has been docked. But I'm sure everybody wants to see the photographs of and the proof. This was a photograph of the breakthrough on December 10th, 2014. Some of the most important people of the project are in this photograph. Jim Nickerson from VTC, Renzo Ciccato, who was the construction manager, Claudio Cimotti, the senior tunnel engineer on the project, as well as a whole other cast of characters that all came together to make this project successful. Really, these are the guys that built the project and made it happen. And with that, we can see here the TBM in place with the bulkhead up in the upper right-hand corner, which is effectively the end. So with that, I'd like to thank you for your attention and open up for any questions.
Luis, thank you so much for that great presentation. As Luis just said, ladies and gentlemen, we'd like to invite questions via the chat panel. We've already had a few questions come in, so I'd like to go ahead and read those off to you. The first one asks, how much ground information was available to the design builder prior to the contract award?
There was an initial campaign that was done by the owner's engineer prior to the RFP being released, and it included a fair bit of information both for the ground that was effectively onshore, as well as a campaign that was performed by barge to do drilling into the lake bed to determine effectively where the best alignment where it was to go. The interesting thing about this project was that there were provisions as well for us as the design builder to perform subsequent ground investigations and effectively verify some of our assumptions. So to answer the question directly, there was a very good amount of information. The borings were sometimes as much as 1,000 feet apart, just due to the difficult nature of drilling from the barge. And we supplemented that information once we were awarded to ensure that we confirmed some of our design assumptions.
Thank you. The next question reads, in the first starter tunnel, was pre-grouting considered as an option for continuing? And if so, why was it deemed unviable?
We did actually try to do some grouting of the ground prior to full abandonment of that alignment. The nature of the ground was such that the gouge material really did not have the structural strength to go ahead and assure us that we could not, we wouldn't be exposing ourselves to risk to go back and mine through it. As gouge material goes, it's not usually effective as a structural fix to do ground treatment.
So was that the main reason to abandon the first starter tunnel?
The main reason that the first starter tunnel was abandoned was mainly due to the instability of the face and exposing the workers to risk. It was just deemed the safer and better option to go ahead and do a new starter tunnel. We worked on that realignment or trying to recover the starter tunnel for the better portion of 6 months before just essentially redesigning and going on a new alignment.
That's great. Thank you so much for answering those questions. That seems to be all we have coming in at this time. Ladies and gentlemen, I'd like to invite you to reach out to Luis with the information on the screen. We're getting thanks coming in the chat now. Luis, would you like to make any final statements?
I'd like to personally thank BTC as well as SNWA. One of the reasons that this project was a great success, in my opinion, is the way that the owner and the contractor and the engineer all worked together to deliver a successful project in spite of some of the challenges that were on the project. The willingness to work together as a team really made the difference, and I would go ahead and highlight that as a lesson learned to all the other owners, contractors, and engineers that work on these type of challenging projects.
That's great, Luis. Thank you so much for your presentation today. And thanks again for joining us for another presentation of the UCA Young Members Group. I'd like to remind all attendees that today's session was being recorded, and within the next 48 hours, you'll receive an email from us with a link back to the website where this presentation will be hosted, so you can view it again at your leisure. So thanks again, everybody, for joining us. We're going to go ahead and end today's session and just be looking for that email with the recorded version within the next day or two. Thanks again, Luis.
Thank you.